To the forces homework problems. So this really deals a lot with Newton's second law and coefficient of friction and things like that. So most of these come from physics classroom. That's why it's called PC. And I gave you a link where you could have gone to the physics classroom to have audio solutions beforehand. At any rate, so this one's an African elephant, has a mass of 6,000 kilograms. Determine the weight in newtons. So weight is equal to m times g. That's very similar to force equals mass times acceleration, which is Newton's second law. So if I have something like that, if you notice, those look the same. Weight is a type of force. It happens to be a gravitational force. Mass is the same. This is any acceleration. This is acceleration due to gravity. So in fact, that's really what we're doing. So that comes out to 58,800 newtons. On the moon, remember, mass is the same for an object. It's the amount of stuff or matter in an object. So it's not like the elephant loses its leg or trunk or something like that. So it's the same amount of mass, but gravity is only 1/6 as strong. So I simply take the 9.8 newtons per kilogram and multiply it by 1/6. And that gets me 9,800 newtons. For PC2, I'm going to look at this problem. So it's asking about the acceleration by an 82 kilogram person who's in a 95 kilogram sled, and that acceleration is 450 meters per second squared. And so it's asking actually about the net force. So in this case, I go back to Newton's second law. The total mass in this case is the sled plus the person. That's 177 kilograms. Acceleration 450 meters per second. So around 79,650 newtons. If I think about that as a free body diagram or force, it literally is just one force in this case. For problem 3, so this has a person whose mass is 52 kilograms experienced a net force of 1,800 newtons at the bottom of a roller coaster loop. So we determine the acceleration. So if I think about the net force is here, the mass is here. So overall, I'm just rearranging Newton's second law. Acceleration is net force over mass, 1,800 over 52. It's around 34.6 meters per second squared. You'd feel like you weigh a pretty heavy amount there. Since gravity is only normally accelerating you at 9.8 meters per second squared, you'd feel heavier than normal. Problem 4 has a couple of steps to it. So I had Nahum in class last year, so I kept his name. I think he's a senior. Yep, he's still in school, so he's a senior this year. So he's essentially pulling on his younger sister in a wagon. So overall, he pulls with a 52 newton force in the wagon. There's 24 newtons of resistance, so that's friction. And the wagon and the sister both have a combined weight of 304 newtons. So first is constructing a free body diagram. Assuming he's pulling horizontally, he's got I call this a push, it really should be a pull, 24 newtons. Friction is the resistance force, that's 24 newtons. Gravity acts down always toward the center of the earth, and this is supposed to say normal force is pointing up. You could say the force of the surface. So the second part is finding the net force. So the net force is simply the applied force from Nahum minus the frictional force. So that's 28 newtons. Now, the second part is asking also, like, what's the acceleration of the wagon? Acceleration is net force over total mass. Well, we just got the net force, that's 28 newtons. But to find the total mass, now I need to revise this formula, which I used earlier. It's a version of Newton's second law. So weight, which is a gravitational force, is equal to m times g. We know the weight of this is 304 newtons. We know g is 9.8 newtons per kilogram. So rearrange that to solve for mass. I get that the mass is 31 kilograms. So now it's simply force over mass, acceleration's 0.9 meters per second squared. Okay. For problem 5 here, which is PC 17, so this is someone skydiving. They've got an 82.5 kilogram mass, experience 118 newtons of air resistance, determine the acceleration at this instant. So I said, hint, draw a free body diagram. Well, I'm going to figure out the weight of the person. That's equal to their mass times 9.8. So they have a weight of about 808 newtons. So when I draw this free body diagram, I've got a longer arrow down than up because the air resistance is only 118 newtons. So now, to find the acceleration, it's net force over mass. So 808.5 minus 118 is 690.5 newtons of net force divided by 82.5 kilograms of mass. So that's around 8.4 meters per second squared. So the reason as the person falls faster and faster, their acceleration gets less and less is because their weight, which is the force downward, stays the same. But as you move faster through the air, the force of drag, or the air resistance force, increases to the point where it would become equal to this gravitational force down. At that point, you're at something called terminal velocity, which is the fastest you can go. And I think I mentioned that term before. Problem 6 on the back has a 0.104 kilogram model rocket accelerating upwards at 45.9 meters per second squared. Determine the net force and then the upward force of the thrust. So overall, again, I drew a free body diagram here. I knew the thrust up would be greater than gravity down. I know the acceleration is 45.9 meters per second squared. I know the mass. So if I do that, I can find the net force. That's just mass times acceleration. But now, to find the force of the thrust, I need to think about the fact that that net force is equal to the thrust minus the gravitational force. So, gravitational force is just m times g. We've seen that a bunch of times now. So 0.104 kilograms times 9.8 newtons per kilogram, that's 1.02 newtons down. So the net force, which is 4.77, is equal to the thrust pointing up minus 1.02 newtons of gravity down. So the thrust is 5.79 newtons. Okay. The last one, PC27, deals with a situation where I'm pushing Mr. Trimner on a floor. There is some friction, and it says that the coefficient of friction between his socks and the floor is 0.35. So first of all, with what's happening, draw a free body diagram. Force the floor up, which is the normal force, gravity down, those two should equal each other. The push to the right, friction to the left. Again, one should be bigger than the other. In particular, since the person's accelerating rightward, the push is larger than the frictional force. So what's the net force on Mr. Trimmer? Well, if he's accelerating at 1.2 meters per second squared, and his mass is 84 kilograms, his net force is 101 newtons. Next is figuring out the force of friction on Mr. Trimner. Well, this is back to a formula we've had. Coefficient of friction is equal to force of friction over normal force. So rearranging that, force of friction equals coefficient of friction times normal force. How much is normal force? Well, okay, normal force is the same as the person's weight. So I have to do that, F equals mg over here. I've done that almost every problem, right? Force of gravity, or the weight, is mg. Here, had to figure out essentially mg. Here, had to figure out mg. So you think that's going to come up on a test? It's going to come up on a test. So at any rate, so I get that, and the normal force and the gravitational force have to be equal on a flat surface like that. And so they're both 823 newtons. So I take 0.35, the coefficient, multiplied by 823 newtons, and that's 288 newtons of friction force. So now, figuring out the force of the push is simply this equation. Net is equal to the push minus the friction. I know the net force is 101. I know the friction force is 288. So therefore the push has to be 389 newtons. That's very similar to what we just did up here in number 6. So hopefully those help. Hopefully you're ready for your test, which we have next Tuesday.